Hello there, and welcome back to the Science Sleepy Minds. And if this is your first time here, congratulations on making what might genuinely be the best decision of your evening. Right now, in this exact moment, you're lying still. Maybe you're tucked under a blanket, or you've got a pillow folded under your arm just the right way, or you're staring at the ceiling with that particular kind of tired where your body is done but your brain hasn't quite gotten the memo yet. You feel completely, utterly motionless. The room is quiet, the air is still. Maybe there's a fan humming somewhere nearby. Everything from your perspective is at rest. And here's the thing, you're catastrophically, hilariously, cosmically wrong about that. At this precise moment, you are spinning through space at roughly 1,000 miles per hour just from Earth's daily rotation alone. You're simultaneously hurtling around the sun at about 67,000 miles per hour. The sun itself, dragging you, your house, your city, your entire planet along for the ride, is screaming through the Milky Way at approximately 514,000 miles per hour. And the galaxy is barreling towards something so enormous and so poorly understood that scientists gave it a name that sounds like a comic book villain, the Great Attractor. You're not still. You've never been still. You will not be still for the entire duration of your existence on this planet, and yet your body registers none of it. You feel nothing. You are, by every sensory measure available to your nervous system, completely at rest. You probably won't survive the full existential weight of what we're about to cover tonight, but don't worry, that's kind of the point. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Tonight we're going deep, and I mean deep, into the true motion of Earth through the galaxy. Not the simplified version from a 6th grade textbook, not the clean circular orbit diagram on a poster in your dentist's waiting room. The real version, the messy, layered, almost incomprehensible cascade of movements that your body is silently performing right now while you try to sleep. If you're watching from somewhere interesting tonight, drop your location and local time in the comments. There is something genuinely lovely about knowing that someone in Norway and someone in New Zealand and someone in a tiny apartment in Tokyo are all, at this exact moment, hurtling through the galaxy together without feeling a single thing. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. We're going to start at the very beginning of the lie, the one that starts the moment you're old enough to notice that the ground beneath your feet feels completely, stubbornly solid. The ground feels like the most reliable thing in your world. It doesn't move, it doesn't shimmy, it doesn't vibrate or tilt or spin. You drop something, it falls straight down. You build a house on it, the house stays put. You drive a nail into it, the nail goes nowhere. For all practical purposes, as every human civilization before the 16th century would have agreed without a moment's hesitation, the ground is the fixed, immovable centre of everything. This was not an unreasonable belief. It was in fact a perfectly rational conclusion drawn from perfect, consistent, daily sensory evidence. Every single morning the sun rose in the east. Every single evening it set in the west. The stars wheeled overhead in their familiar patterns. The moon moved across the sky in its stately arc. Everything in the heavens was clearly, obviously moving, and you, equally clearly and obviously, were not. Ancient Greek astronomers built entire mathematical systems on this intuition, elaborate models of crystalline spheres nested within each other, each carrying a celestial body around the fixed Earth at its centre. These models were, in their own way, engineering marvels. They could predict planetary positions. They could calculate eclipses. Historians still argue whether the geocentric model persisted as long as it did because of religious dogma, as the popular story goes, or simply because it worked well enough for every practical purpose anyone needed it for. The uncomfortable truth is that the geocentric model lasted for nearly 2,000 years, not because people were foolish, but because your senses are genuinely, reliably wrong about motion, at scales larger than your immediate surroundings. Your inner ear can detect acceleration, sudden changes in speed or direction, but constant velocity, smooth, unchanging, perfectly steady movement, your nervous system is completely blind to it. You feel zero sensation from Earth's rotation because it's constant. You feel zero sensation from Earth's orbital speed because it's constant. You are right now a passenger in a vehicle moving at speeds that would reduce any human-made object to vapor if it struck anything solid. And your body is reporting back. Absolutely nothing to see here. Very calm, very still, maybe getting a little sleepy actually. That is the magnificent lie we have all been living since birth. And tonight we're going to peel it back, slowly, gently, layer by layer, until you have a picture of your true motion through the cosmos that is so complete and so quietly astonishing that the ceiling you're staring at right now will look subtly different to you by the time we're done. We'll start with the smallest movement and work outward, and each layer you'll find is stranger and faster and more beautifully bizarre than the one before it. By the time we reach the outermost layer, the one that involves the entire observable universe and a radar gun made of ancient light, you will either be deeply, peacefully asleep or lying very still with extremely wide eyes. Both are acceptable outcomes. The first movement, the most intimate one, the one that governs your entire sense of day and night, is the spin. Earth rotates on its axis once every 24 hours. You know this. It's the kind of fact that gets absorbed so early in childhood that it stops feeling like information and starts feeling like furniture, just something that's always been there, taking up space in the background of your mind. But let's actually sit with it for a moment, because the spin is stranger and more consequential than most people ever pause to appreciate. The axis that Earth spins on is not straight up and down relative to its orbit. It's tilted at about 23.4 degrees, and this tilt, this one stubborn, ancient lean, is responsible for every season you've ever experienced. Every extra hour of summer daylight that ever made you feel inexplicably cheerful. Every grey, low-sun December afternoon that ever made you want to hibernate. The tilt isn't a small cosmetic detail. It's one of the central organising facts of life on Earth. Here's where the spin gets interesting in terms of speed. The Earth is roughly 24,900 miles around at the equator. It completes one full rotation in 24 hours. So if you're standing on the equator right now, if you're watching this from somewhere near the equatorial belt, hello, greetings from your fellow hurtling passengers. The ground beneath your feet is moving at about 1,038 miles per hour. That is faster than a commercial jet aircraft at cruising speed. You are, technically, already supersonic, and you haven't done a single thing to earn it. Now, if you're not at the equator, the number drops, but not to zero. If you're at a latitude of about 45 degrees, which covers a huge swath of the inhabited northern hemisphere, think southern France, northern California, the northern islands of Japan. You're spinning at around 733 miles per hour. If you're in London or Calgary or Moscow, closer to 650 miles per hour. Even at the poles, where the rotational speed drops essentially to zero in terms of linear velocity, you're still spinning, just turning in place, very slowly, like someone who fell asleep standing up at a very boring party. The reason you feel none of this is one of the most elegant features of physics, and also one that ancient philosophers didn't have the framework to understand. You're not just on a spinning Earth, you're part of the spinning Earth. The air around you spins with you. Your coffee spins with you. If you toss a ball straight up, it comes back down to your hand rather than landing 30 feet to the west, because the ball is also spinning with you. Everything in your immediate environment is locked into the same rotation, all moving together, all perfectly synchronized in a way that your senses have absolutely no mechanism to detect. This is called inertia, the tendency of objects in motion to stay in motion unless something external acts on them. You are in motion. You have always been in motion. Your entire experience of life has occurred at rotational speeds that would be considered extreme by any standard outside of geophysics, and your body has registered precisely nothing. There is, however, one tiny charming piece of evidence of the spin that you can observe if you know where to look. It's called the Coriolis effect, the slight deflection that Earth's rotation imparts on objects moving over long distances. In the northern hemisphere, large-scale air circulation, hurricanes, weather systems, the direction large storms rotate, curves to the right. In the southern hemisphere, it curves to the left. This is the rotation making itself visible, leaving its fingerprints on the atmosphere for distances large enough that the effect accumulates into something measurable. The popular claim that this effect also determines which way your toilet drains or your sink swirls, it's worth knowing, is mostly a myth. The Coriolis effect is far too weak at those scales to overcome the random swirling introduced by the shape of the drain, the residual motion of the water, and the direction it was filled. Scientists still debate the precise threshold at which Coriolis deflection becomes the dominant factor, but it's safe to say that your bathtub is not a reliable piece of evidence for Earth's rotation. What is a reliable piece of evidence is the Foucault pendulum, a long, heavy pendulum that, when set swinging, appears to gradually rotate its plane of swing over the course of a day. It's not actually rotating. It's swinging in a fixed plane relative to the stars. The Earth is rotating beneath it. In 1851, Léon Foucault hung one inside the Pantheon in Paris and demonstrated to a public that could see it with their own eyes that the ground beneath their feet was moving. There's something poetic about the fact that it took a very long string and a very heavy ball to make the invisible visible. The tilt that creates seasons has another consequence that most people don't often think about. It's not perfectly stable. Earth's axial tilt doesn't stay fixed at 23.4 degrees. It wobbles very slowly over cycles of approximately 41,000 years, between about 22.1 and 24.5 degrees. When the tilt is more extreme, the seasons are more extreme too. Hotter summers, colder winters, sharper contrasts between them. When the tilt is shallower, the seasons moderate. This wobble, combined with other slow variations in Earth's orbit, creates long climate cycles, the Milankovitch cycles, that are believed to pace the coming and going of ice ages over geological time. Here's a fringe tidbit that doesn't get much airtime. Some researchers have proposed that the Moon is the reason Earth's axial tilt is as stable as it is. The Moon's gravitational influence acts as a kind of stabilizer, damping the wobble and keeping it within that relatively narrow 22 to 24 degree range. The implicit suggestion that without the Moon, Earth's tilt might have swung wildly over time, making the climate far less predictable, potentially making the long-term stability that complex life requires far less achievable, is one of those ideas that sits in the back of your mind and refuses to entirely leave. You're spinning. At this very moment, as your eyes grow heavier, the planet is turning, and it will keep turning all night, all year, all century, patient and unhurried, as it always has been. Now add a second motion on top of the spin, and notice how quickly the numbers start climbing. While Earth is rotating on its axis, it's also travelling in a great loop around the Sun. This is the orbit, the motion that creates the year, that turns the calendar pages, that brings the meteor showers back on schedule, and sends the swallows back north every spring. It's the one cosmic motion that human beings noticed first, measured longest, and argued about most ferociously throughout recorded history. But let's clear up the first and most persistent misconception immediately. The orbit is not a circle. This surprises people more than it probably should. The image most of us carry in our heads, the one from every solar system diagram ever drawn in a classroom or printed in an encyclopedia, shows Earth tracing a perfect, smooth, round circle around the Sun sitting precisely at the centre. It's clean. It's satisfying. It looks exactly like something should look when it's behaving itself properly. And it is almost entirely wrong. Earth's orbit is an ellipse, a slightly squashed oval, with the Sun located not at the centre, but at one of two focal points offset from the centre. In Earth's case, the ellipse is fairly close to circular. The difference between the closest point and the farthest point is not dramatic enough to be visible to the naked eye in most diagrams, which is part of why the circle myth persists so stubbornly. But the difference is real, and the consequences of it show up in your life in ways you might not have connected before. The closest point in Earth's orbit to the Sun is called perihelion. It occurs in early January, specifically around January 3rd or 4th, varying slightly from year to year. At perihelion, Earth is about 91.4 million miles from the Sun. The farthest point, called aphelion, occurs in early July, when Earth is about 94.5 million miles away. That's a difference of roughly 3 million miles, a number that sounds significant until you remember we're talking about an average distance of 93 million miles, making it about a 3% variation. Here is the consequence that tends to mildly blow people's minds. The Northern Hemisphere's winter, the cold, dark, miserable season, happens when Earth is actually closest to the Sun. Not farthest. Closest. The cold of January in London or Chicago or Moscow is not because those places are farther from the Sun in January. They are literally closer to the Sun in January than in June. The coldness of winter in the Northern Hemisphere comes entirely from the axial tilt causing the sunlight to arrive at a shallower angle and for fewer hours per day, not from actual proximity to the star. This also has a fun corollary. Because Earth is slightly closer to the Sun in January than in July, it moves slightly faster in January. This is the other aspect of elliptical orbits that the circle diagram never captures. Orbital speed is not constant. Planets move faster when they're closer to the star and slower when they're farther away. This relationship was formalized by Johannes Kepler in his second law of planetary motion in 1609, though it took Isaac Newton's gravitational theory to explain why it worked. Earth in January near perihelion is moving at about 67,750 miles per hour. Earth in July near aphelion is closer to 65,500 miles per hour, a difference of about 2,000 miles per hour, and yet the year divides itself into months of very similar length, so nobody notices. The ellipse also means that the solar year, the time it takes Earth to complete one full orbit, is not an exact clean number of days. It's approximately 365.25 days. That messy quarter day is why we invented the leap year. Add one extra day every 4 years to keep the calendar aligned with the actual orbit. But even that fix isn't quite right. The year is actually 365.2422 days, not 365.25, so 3 leap days are skipped every 400 years under the Gregorian calendar system. Historians still argue about whether the original Julian calendar reform, which established the leap year but without this finer correction, caused more confusion than it solved in the centuries before the Gregorian reform of 1582. The speed of Earth's orbital journey, averaging around 66,600 miles per hour, is astonishing on its own terms. At that speed, you could travel from Earth to the Moon in about 3.5 hours. You could get from Earth to Mars at its closest approach in a matter of days, if you could survive the vacuum and radiation and could somehow stop without any brakes. The entire surface of the Earth is whipping through space at a clip that makes every human speed record look completely inconsequential, and it does so with such flawless, frictionless regularity that your only evidence of it is the slow crawl of seasons and the reliable return of your birthday. There's a beautiful fringe thought that occasionally appears in cosmological discussions. Because Earth moves about 1.6 million miles through space every day in its orbit, no 2 sunrises in your life have ever occurred at the same point in space. Every morning you've ever watched the sun come up, you are in a different location in the cosmos than you had ever been before or will ever be again. Your entire life has been a single, unrepeated trajectory through space, and not one moment of it has ever happened twice. That's either deeply comforting or mildly vertiginous, depending on your mood and the hour. At this point in our journey, you have 2 motions stacked on top of each other, spinning it up to 1,000 miles per hour, orbiting at 67,000 miles per hour. You're a particle on a spinning top that is itself looping around a fire, and we've not yet begun to describe the larger motion that carries all of it, the spin, the orbit, the fire itself, through something vast enough to make both numbers look, by comparison, almost quaint. The Sun is not staying put while Earth orbits it. That's the next layer, and it changes everything. This is the part that the solar system diagram on the classroom wall most deeply fails to convey. The standard image shows the Sun at the centre, the planets orbiting around it, and the whole arrangement sitting inside a large empty white space with no reference point to anything outside. The implication of the image, even if the textbook caption technically denies it, is that the Sun is fixed. It is the anchor. Everything else moves, but the Sun stays. This Sun is moving at approximately 514,000 miles per hour. Let's hold that number for a moment. 514,000 miles per hour. For context, that is about 0.07% of the speed of light. Not a relativistic speed by any serious measure, but in terms of anything your imagination was built to comprehend, it is staggering. The fastest human-made object ever built, the Parker Solar Probe at its closest solar approach, reaches speeds of around 430,000 miles per hour, and that required falling deep into the Sun's gravity well to achieve it. The Sun is exceeding that speed all the time, while also creating the gravity well, while also dragging 8 planets and their moons and a vast surrounding cloud of comets and asteroids along with it. This motion of the Sun, and by extension the entire solar system, through the Milky Way is called the galactic orbit. The solar system is orbiting the centre of the galaxy, a vast gravitational engine lurking in the direction of the constellation Sagittarius, roughly 26,000 light-years away. Every atom on Earth, every ocean, every mountain range, every building ever constructed, every person who has ever lived and died, all of it is locked into this grand sweeping orbit around the galactic centre. The galactic centre itself is anchored by something called Sagittarius A star. which is a supermassive black hole with a mass approximately 4 million times that of our Sun. It is not the only thing providing gravitational pull on the solar system's orbit. The combined mass of hundreds of billions of stars, enormous clouds of gas and dust, and the still debated but powerfully influential presence of dark matter all contribute. But Sagittarius A star is the central landmark, the gravitational kingpin around which the entire galaxy rotates. The Sun completes one orbit around the galactic centre in approximately 225 to 250 million years, a span of time called, not without a certain poetry, the cosmic year or the galactic year. The solar system has completed this orbit about 20 times since it formed, which means Earth has a history measured not just in billions of solar years, but in approximately 20 full cosmic years. Now here is where the intuitive breakdown really begins to set in. Unlike Earth's orbit around the Sun, which happens in the relatively well-behaved plane of the solar system, the solar system's motion around the galactic centre is embedded in a three-dimensional structure of extraordinary complexity. The Milky Way is not a flat, perfectly ordered clockwork. It is a barred spiral galaxy, and we will spend more time on what that means and how bizarre it actually is. And the solar system's path through it is not a clean ellipse. It is a messy, bobbing, weaving trajectory that passes through regions of higher and lower stellar density, through the arms and the interarm spaces of the galaxy, through zones where cosmic ray bombardment is intense, and zones where it is relatively quiet. The historical fact that anchors this section is worth savouring. The realisation that the Sun moves was one of the most hard-won achievements in the history of astronomy. For most of recorded history, even after Copernicus and Galileo had established that the Earth orbited the Sun itself was still assumed to be stationary, the fixed centre of the universe, just not the centre of the solar system. It was William Herschel, the same 18th century astronomer who discovered the planet Uranus, who first produced observational evidence that the Sun was moving. By carefully measuring the apparent motions of nearby stars and noticing that stars in one region of the sky seem to be gradually spreading apart, while stars in the opposite region seem to be converging, he correctly deduced that the Sun was moving toward the region of spreading, a point he called the solar apex, in the direction of the constellation Hercules. It was careful, methodical detective work performed with the tools of the 1780s, and it was correct in all essential respects. The quirky tidbit worth noting here is that for a brief period in the late 19th century, some astronomers seriously proposed the existence of a counter-sun, a dark, massive body orbiting the galactic centre on the opposite side from our Sun, gravitationally acting as a kind of counterweight. The idea was motivated by attempts to explain certain anomalies in stellar motion data, and was entertained in respectable journals before better data made it unnecessary. Historians of science still debate whether this episode represents a productive avenue of inquiry that simply turned out to be wrong, or an early example of cosmological wishful thinking dressed up in mathematics. What Herschel started, subsequent generations of astronomers refined with increasingly precise instruments. By the 20th century, it was established not just that the Sun was moving, but that it was moving around the galactic centre, in a grand orbit, in a galaxy that contained hundreds of billions of stars all doing the same thing, orbiting, weaving, bobbing through a structure so large that our best observational tools today are still working to map its outer edges, and so the numbers on your cosmic speedometer keep climbing. You're spinning at 1,000 miles per hour. You're orbiting the Sun at 67,000 miles per hour. You're now also riding the Sun as it races around the galactic centre at 514,000 miles per hour. And we have still not added the final, largest motion, the one that carries the entire galaxy itself. But first, let's talk about that cosmic year in more detail, because the last time Earth was in roughly this same spot in the galaxy, the world looked absolutely nothing like it does tonight. 225 million years. Say it slowly and notice the way it dissolves into abstraction almost immediately. The human brain is genuinely not built to hold that number. We have passable intuitions about decades. Most of us can feel the difference between 10 years ago and 20 years ago in our own lives. We can stretch, with some effort, to centuries. 100 years ago, there was a world war. There were no commercial airplanes. Your great-grandparents might have been children. We can even gesture at millennia. 5,000 years ago, ancient Egypt was a going concern. 10,000 years ago, humans were just beginning to build the first permanent settlements. But 225 million years? That is not an extension of human intuition. That is a complete departure from it. The most useful thing you can do with that number is not to feel it, but to populate it with landmarks. When the solar system was last in this approximate position relative to the Milky Way galaxy, completing the previous cosmic year and beginning this one, the year on Earth was roughly the early Triassic period. The Permian-Triassic extinction event had just occurred, or was in the process of concluding. This was the most catastrophic mass extinction in Earth's history, not the one that killed the dinosaurs, which was comparatively modest, but a much earlier, much more devastating event that wiped out an estimated 90 to 96% of all marine species and around 70% of terrestrial vertebrate species. The world was rebuilding from near total biological collapse. The first true dinosaurs wouldn't evolve for another 20 to 30 million years. The first mammals were just beginning to appear, tiny and shrew-like and deeply unimpressive. The continents, still joined into the supercontinent Pangaea, were beginning the slow, grinding process of drifting apart. That is one cosmic year ago. The dinosaurs that would come to dominate the planet and hold it for 165 million years from their origin to their extinction represent less than a single cosmic year in duration. The entire reign of the dinosaurs fits inside the time it takes Earth to complete one trip around the galaxy. Half a cosmic year ago, roughly 112 million years ago, the Cretaceous period was underway. Dinosaurs were at their peak diversity. Flowering plants were just beginning to spread across the planet. Small, primitive mammals were surviving in ecological niches too small and unpleasant for dinosaurs to bother with. The continents had drifted into roughly recognizable shapes, though still quite different from today's geography. A quarter cosmic year ago, about 55 to 60 million years ago, the dinosaurs had been extinct for approximately 10 million years, and the first primates had appeared. Humans, in any form even remotely recognizable, were still more than 50 million years in the future. In other words, the entire history of life on Earth, from the first bacterial cells in ancient oceans, through the Cambrian explosion of multicellular life, through the age of fishes and the colonization of land, through every era of dinosaur dominance, through the rise of mammals and primates and humans, through all of recorded human history, including every empire and every invention and every war and every beautiful piece of music ever written. All of this has occurred in less than 20 cosmic years. Earth is roughly 4.5 billion years old, which is about 20 cosmic years. This is one of the great yardsticks of deep time, and it has a practical use beyond the purely philosophical. Astrobiologists and geologists studying the long-term evolution of Earth's climate and biosphere sometimes use the galactic orbit as an organizing framework, asking whether Earth's position within the galaxy during different cosmic years correlates with the pattern of its ice ages, its extinction events, its periods of unusual warmth or biological productivity. Historians of science still argue whether the correlations being found in this research represent genuine causal relationships, or are the inevitable result of finding patterns in data rich enough to produce them accidentally. The quirky fringe idea here is delightful in its audacity. Some researchers have proposed that the timing of major evolutionary leaps on Earth, the Cambrian explosion, the emergence of complex multicellular life, the dramatic diversification events that punctuate the fossil record, might correlate with specific phases of the galactic orbit, particularly with the solar system's passage through regions of higher cosmic ray exposure or denser interstellar gas. The hypothesis, sometimes called cosmic influence on evolution, remains very much on the fringes of mainstream biology, but it has attracted enough attention from serious researchers to be taken seriously as a question, if not yet as an answer. There's something both humbling and quietly comforting about the cosmic year as a concept. It suggests that Earth's history is not random, that there is a larger rhythm to it, a slower beat that underlies all the faster rhythms of seasons and orbits and human generations. Your life, impossibly short on this timescale, is nonetheless part of this rhythm. The atoms in your body are mostly ancient, carbon forged in stars that lived and died before the sun was born, hydrogen as old as the universe itself. And those atoms are currently making their way around the Milky Way, as they have been for billions of years, as they will continue to do long after the particular arrangement of them that constitutes you has dispersed back into the world. The Milky Way is very patient with its passengers. We are now about 5 layers into Earth's motion, and the layers keep adding. Spin, orbit around the sun's orbit around the galaxy, the cosmic year, and we haven't yet described the shape of the structure we're orbiting through, which turns out to be considerably stranger than the elegant spiral everyone imagines. When you picture the Milky Way, you probably picture a spiral, a smooth, elegant pinwheel of stars, gracefully curved arms sweeping outward from a bright central core, the whole thing flat and neat like a watch mechanism viewed from above. It's a beautiful image. It appears on book covers and screensavers and observatory posters. It is also, in a number of important ways, quite misleading. Let's start with the most fundamental problem. We can't actually see the Milky Way's shape from the outside. This seems obvious when stated plainly, but its implications are easy to underestimate. We are inside the Milky Way. We are embedded in it, roughly 2/3 of the way out from the centre, tucked inside one of its spiral arms. Trying to determine the overall shape of the galaxy from our position is like trying to determine the shape of a forest while you're standing in the middle of it. You can see trees in every direction. You can notice patterns in the local arrangement, a clearing here, a denser clump there. But the overall shape of the forest, the way it looks from above, the pattern of its edges, all of that requires a perspective you simply don't have. Everything we know about the Milky Way structure has been assembled indirectly, through radio astronomy, through infrared observations that can penetrate the dust clouds that block visible light, through the tracking of stellar motions, through the behaviour of gas and molecular clouds. The current best picture we have of the Milky Way is not an observation, it's a model built from thousands of data points and continuously revised as new data arrives. And what that model tells us is this: the Milky Way is not a classic spiral galaxy, it's a barred spiral galaxy. At the centre, instead of a smooth round core, there is an elongated bar of stars, a long dense structure estimated at about 27,000 light-years in length, oriented at an angle to the plane of the spiral arms. This bar was suspected for decades but confirmed with confidence only in the early 2000s through infrared surveys that could see through the intervening dust. The bar rotates as a rigid structure, and the spiral arms emerge from its ends rather than from the centre directly. The spiral arms themselves, the Milky Way has two major arms, the Scutum Centaurus arm and the Perseus arm, plus several secondary or minor arms, are not uniform, continuous features. They are more like density waves, regions where stars and gas are compressed into higher density as the galaxy rotates, creating the visual impression of permanent arms, even though individual stars drift in and out of them over time. Our solar system currently sits in or near the Orion Arm, which is a shorter, minor arm or spur between the two major arms. Historians of galactic astronomy still argue about whether the Orion Arm should be classified as a true spiral arm or merely a fragmented spur, and the question is less settled than most introductory textbooks imply. Then there's the warp. The Milky Way's disk is not flat. It is warped, bent upward on one side and downward on the other, like a vinyl record that's been left too close to a heat source. The warp was identified in the 1950s through radio observations of neutral hydrogen gas and has been confirmed and refined many times since. The cause of the warp is not definitively established, though the leading candidates include the gravitational influence of the Large and Small Magellanic Clouds, the two smaller galaxies that orbit the Milky Way, and interactions with streams of dark matter. The Gaia satellite, launched in 2013, has provided extraordinary new data on stellar positions and motions throughout the disk, and researchers analysing Gaia data are still working through its implications for our understanding of the warp's structure and origin. The size of the Milky Way is itself a subject of ongoing revision. For a long time, the standard figure given for the galaxy's diameter was about 100,000 light-years. More recent estimates, taking into account the extended outer disk and the warped edges, have pushed that figure to 150,000 or even 200,000 light-years. A 2019 study suggested the disk extends even farther than previously thought, with star-forming regions detectable at distances from the centre that were previously considered the empty outer edges. The Milky Way keeps getting bigger as our instruments get better. The practical effect of all this on Earth's galactic motion is that we're not orbiting through a simple, smooth medium. We're moving through a structured, lumpy, warped, bar-dominated, arm-threaded galaxy where the density of stars, gas, dust and cosmic ray sources varies significantly from one region to the next. Our current position in the relatively uncrowded interarm region is, as it turns out, rather pleasant. Fewer close stellar neighbours, lower cosmic ray exposure, less disruption to the long-term orbital stability that complex life requires. Spending time inside a dense spiral arm is, on the other hand, a considerably more violent and energetically eventful experience. The fringe tidbit that earns its place here: there are astronomers who have proposed seriously and in peer-reviewed literature that the Milky Way may not have 4 spiral arms as long assumed, but could have as few as 2 major arms, with what we thought were additional arms being fragments, spurs, or regions of confused star formation, rather than true galactic scale structures. The number of arms in our own galaxy remains, in 2025, a genuinely unsettled question, which is remarkable when you consider how much time and energy has gone into answering it. You're travelling through this warped, bar-spiraled, lumpy galaxy right now, not in a clean orbit, but in a weaving, oscillating path that dips above and below the galactic plane as it goes. Which brings us to the next motion, the bob. There is a motion in Earth's cosmic journey that almost nobody mentions in casual summaries of how the solar system moves, and it might be the most visually striking one if you could somehow watch it from a great enough distance. The solar system bobs as it travels around the Milky Way in its vast 225 million year orbit. This solar system doesn't stay in a fixed plane. It oscillates, slowly, rhythmically, up and down through the galactic plane like a horse on a fairground carousel. It dips below the central plane of the galaxy, then rises above it, then dips below again. The period of this oscillation, the time it takes to complete one full up-down cycle, is approximately 60 to 70 million years. The amplitude, the maximum distance above or below the mid-plane that the solar system reaches at the extremes of its oscillation, is roughly 200 to 300 light-years. 200 to 300 light-years is not a trivial distance. For comparison, the nearest star to the Sun, Proxima Centauri, is about 4.2 light-years away. The solar system's up-down bob takes it through regions of space that are 50 to 70 times more distant than our nearest stellar neighbour. Over the course of a single galactic orbit, the solar system bobs up and down roughly 3 to 4 times. Right now, as best as current measurements indicate, the solar system is slightly above the galactic midplane by about 50 to 80 light-years and currently moving upward away from the plane. The midplane, by the way, is not just an arbitrary geometric reference line. It is the region of highest density in the galactic disk. The densest concentrations of gas, dust, molecular clouds, and young, energetic, massive stars are clustered near the midplane. Moving away from it, as the solar system currently is, means moving into relatively calmer, less dense galactic territory. The reason for this bobbing motion lies in the gravitational distribution of the galaxy. The bulk of the galaxy's mass is concentrated in and near the midplane. When the solar system drifts above or below it, the gravitational pull from that concentrated mass acts like a restoring force, pulling the solar system back toward the plane. But the solar system has momentum, so it overshoots, passes through the midplane, continues to the other side, decelerates as it moves away from the mass concentration on that side, stops, and begins moving back. It's the same physics as a pendulum, gravity acting as a restoring force, momentum causing oscillation, energy gradually dissipating over unimaginable timescales. This bobbing has attracted significant scientific attention because of what it might mean for Earth's biological history. The galactic midplane is not only the densest region for gas and dust, it is also the region with the highest density of molecular clouds. The enormous cold dark clouds of gas and dust that are the birthplaces of stars. Passing through or near these clouds could expose the solar system to elevated levels of cosmic rays, could potentially perturb the Oort cloud, the vast reservoir of comets in the outer solar system, and could have subtle effects on Earth's climate and bombardment rate. Some researchers have proposed a hypothesis, fascinating, controversial, and not yet settled, that the timing of the solar system's crossings through the galactic midplane correlates with the timing of mass extinction events on Earth. The numbers are suggestive. Mid-plane crossings occur roughly every 30 to 35 million years in each direction, and there is a cluster of proposed extinction events and cosmic bombardment episodes at roughly similar intervals in the geological record. The most famous of these, the impact event that ended the Cretaceous period and killed the non-avian dinosaurs, falls within a period when the solar system was passing through a denser region of the galactic disk. Historians of science and geologists still argue vigorously whether this correlation represents genuine causation, coincidence in a dataset large enough to produce spurious patterns, or something in between. The fringe idea worth mentioning in this context is more provocative. some researchers have suggested that the galactic bobbing cycle, combined with the periodicity of a large comet showers, might have acted as a pacemaker for evolution on Earth, not just causing extinction events but also, in the aftermath of those events, creating the ecological openings that allowed new forms of life to diversify explosively. Under this view, mass extinctions are not purely catastrophic endpoints but resets. Brutal, indiscriminate resets, certainly, but ones that open space for subsequent biological innovation. The bobbing of the solar system through the galaxy might, on this interpretation, be one of the deep rhythms underlying the entire pageant of complex life on Earth. There is something quietly unsettling about this idea. The fate of the dinosaurs, the rise of the mammals, the eventual existence of human beings, might all of these hinge in some small way on the fact that the solar system was 66 million years ago, passing through a particularly eventful stretch of its galactic bobbing cycle. The chain from galactic structure to Cretaceous geology, to biological extinction, to mammalian diversification, to primate evolution, to you, lying in your bed right now, is impossibly long and improbably specific, and yet the links are there, connecting you to a cosmos that was shaping your existence long before your species existed. The bob is slow, one full oscillation in 60 to 70 million years. You won't notice it in a lifetime, or in 1,000 lifetimes, but it is happening right now as you settle towards sleep, the solar system moving gently upward through the galaxy like something that has absolutely no idea how grand its own motion is. Between the stars, in the vast dark gaps that separate solar system from solar system, galaxy from galaxy, space is not empty. This surprises people the first time they really sit with it. Empty space is a powerful intuition, one that the word space itself encourages. But the reality is that interstellar space is filled with tenuous, diffuse material. Gas, dust, cosmic rays, and magnetic fields, all threaded through and shaped by the gravity and radiation of the stars embedded within it. The solar system currently resides in a region of interstellar space called the local bubble, and the name is almost cozy, which makes what it actually is somewhat jarring. The local bubble is an enormous, roughly spherical or irregularly shaped cavity in the interstellar medium, spanning approximately 300 light-years across. Inside it, the gas density is extraordinarily low, about 10 times lower than the average gas density in the galactic disk outside it. The temperature of this gas is extremely high, millions of degrees Kelvin, making it a very hot, very thin plasma. Outside the bubble, the interstellar gas is cooler and much denser, and the boundary between the bubble interior and the surrounding medium is a kind of thin shell of compressed gas and dust. The local bubble was carved out by a series of supernova explosions, the violent deaths of massive stars that occurred in our galactic neighborhood over the past 10 to 20 million years. Each supernova blasted an enormous sphere of hot gas outward, and the cumulative effect of multiple supernovae in a small region of the galaxy over a few million years was to excavate this large, hot, nearly empty cavity. The stellar population responsible for these supernovae was a moving association of young, massive stars, now called the Scorpius-Centaurus Association, which was passing through the neighborhood at the time and has since moved on. The solar system has been inside the local bubble for somewhere between 5 and 10 million years, having drifted into it as the bubble expanded outward and the solar system's own orbit brought it into this region. Before entering the bubble, the solar system was moving through denser, cooler interstellar gas, and that difference may have had consequences for Earth's climate and the structure of the heliosphere, the magnetic bubble created by the solar wind that surrounds the solar system, and provides some protection from cosmic rays. Within the local bubble, the solar system is not entirely in featureless emptiness. It currently sits inside an even smaller, denser structure called the local interstellar cloud, sometimes called the local fluff, which is a name that carries an interesting tonal dissonance given the context. The local fluff is a warm, tenuous cloud of hydrogen and helium gas, about 30 light-years across, that the solar system has been passing through for about 45,000 to 150,000 years. The cloud is warm, around 6,000 Kelvin, which makes it technically warm plasma rather than neutral gas, and it interacts with the outer boundary of the heliosphere in ways that are actively being studied. At the edge of the local fluff, measurements from the Voyager spacecraft, which have now both crossed into interstellar space, making them the only human-made objects to have done so, suggest a more complex boundary structure than was predicted. The interaction between the solar wind and the interstellar medium at the heliopause is not a clean, sharp transition, but a messy, dynamic interface that is sensitive to changes in both the solar wind and the surrounding interstellar gas. As the solar system moves through the local fluff and eventually into the different gas environment beyond it, this interface will change, and the effects on the heliosphere's size and shape, and potentially on the flux of cosmic rays reaching the inner solar system, could be significant on timescales of tens of thousands of years. The historical fact here is worth pausing on. The discovery of the local bubble came gradually through the second half of the 20th century, as radio astronomers and X-ray satellite observations began to reveal the large-scale structure of the interstellar medium in our galactic neighbourhood. The term local bubble was not widely used until the 1980s, and the full picture of its size, shape and origin has been assembled piecemeal over decades. The Gaia satellite's precise mapping of stellar positions and distances has contributed enormously to understanding the distribution of dust and gas that outlines the bubble's structure. The quirky fringe note, a 2022 study, proposed that not just the local bubble, but most of the known molecular clouds in our galactic neighbourhood, including many of the star-forming regions that are currently actively producing new stellar systems, are located on or near the expanding shell of the local bubble. Under this interpretation, the supernovae that created the local bubble may have triggered the star formation in several nearby stellar nurseries, including the regions in Taurus, Perseus, Orion, and other constellations that have long been studied as active sites of stellar birth. The local bubble, under this view, was not just an evacuated cavity but a generator, its expanding shell compressing interstellar gas ahead of it, and triggering the formation of stars that did not yet exist when the bubble began to expand. Historians of molecular cloud science still debate whether this cascading star formation model fully accounts for the data, or whether other triggering mechanisms are also at work. You're inside a cosmic bubble, a giant, hot, thin-walled cavity blown by stars that exploded millions of years before any human existed. And within that bubble, you're drifting through a warm wisp of plasma that smells, if anything in space smells, of nothing at all. There is a point in the sky toward which the entire solar system is drifting, and it has a name. It is called the solar apex, and it sits in the direction of the constellation Lyra, specifically near the bright star Vega, which is one of the most famous stars in the Northern Hemisphere sky, and the star around which the entire premise of Carl Sagan's novel Contact was built. The solar system is not, of course, moving toward Vega specifically. Vega is about 25 light-years away, and the solar system is not on a collision course with it. The solar apex is simply the point on the celestial sphere that corresponds to the direction of the Sun's current motion, the gravitational resultant of all the forces and velocities that define the solar system's trajectory through the local neighbourhood of the galaxy. Stars near the solar apex appear, over long enough timescales, to gradually spread apart as the solar system approaches them, in the same way that trees ahead of you appear to spread apart as you walk toward them. Stars near the opposite point on the sky, the solar antipex in the direction of the constellation Columba, appear to gradually converge. This apparent spreading and converging is called stellar parallax at the motion scale, not to be confused with the annual parallax used to measure stellar distances, which is caused by Earth's orbital motion around the Sun. The solar motion parallax caused by the Sun's actual movement through space operates over years and decades rather than months, and its effects are subtle enough that they require careful long-term astrometric observations to detect in individual stars, though they are clearly visible in aggregate statistical analyses of stellar proper motions. The speed of the solar system's motion toward the solar apex is, in the reference frame of the local stars, the nearby stellar neighbourhood, approximately 12 to 20 kilometers per second, depending on exactly which stars are used to define the local standard of rest. This is much smaller than the 514,000 miles per hour galactic orbital speed because it represents the solar system's peculiar velocity, its deviation from the average motion of the local stellar neighbourhood, rather than the total speed relative to the galactic centre. The local standard of rest is itself moving around the galactic centre, and the Sun's peculiar velocity is its individual wiggle relative to that collective motion. The concept of peculiar velocity is important because it reveals that the solar system is not following a perfectly smooth average galactic orbit. It has its own idiosyncratic quirks. It moves slightly faster or slower than average in various directions, wobbles around the mean path, and has a net drift in the solar apex direction that reflects some combination of its formation history, gravitational perturbations from nearby massive objects over its lifetime, and the general dynamical state of the local galactic disk. This motion toward Vega has a history in the study of the solar system that is both scientifically interesting and has been subject to some interesting cultural distortions. William Herschel's identification of the solar apex in the 1780s, mentioned earlier, was a genuine landmark, the first evidence that the Sun was not stationary relative to the stars. The solar apex is not always presented in exactly the direction of Vega, because the precise direction depends on the reference frame and the set of stars used for analysis, and the best current measurements place it near but not exactly at Vega. Historians of astronomy still argue about the exact interpretation of Herschel's original analysis, and whether he was as close to the modern value as is sometimes claimed. The peculiar velocity toward the solar apex has a direct bearing on how the interstellar environment around the solar system will change over the next few 100,000 years. As the solar system drifts in the Vega direction, it will gradually move out of the local fluff cloud currently surrounding it into the next patch of interstellar medium, and what that next patch is like, whether it is denser or more tenuous than the local fluff, whether it contains higher or lower cosmic ray fluxes, whether it will compress or expand the heliosphere, is a matter of active research with no definitive answer yet. The fringe tidbit here involves the concept of interstellar weather, a genuine research field, not a metaphor. As the heliosphere moves through changing interstellar environments, the conditions inside it change too. A denser interstellar medium would compress the heliosphere inward, reducing its protective effect against galactic cosmic rays. A very dense cloud encounter, should the solar system drift into a cold, dense molecular cloud, which it will occasionally do on longer timescales, could potentially expose the Earth to significantly elevated cosmic ray flux. with consequences for the chemistry of the upper atmosphere and potentially for the climate. Some researchers have attempted to correlate the timing of ancient cosmic ray signatures preserved in Antarctic ice cores and lunar samples with the timing of hypothesized cloud crossings in the solar system's recent past. There is something gently surreal about the solar apex that becomes apparent when you sit with it in the dark. Vega is a real star. You can look up on a clear summer evening in the northern hemisphere and see it, bright and blue-white, the brightest star in Lyra, the one the alien signal comes from in the movie Contact, the one that serves as the North Star during an earlier phase of Earth's axial precession cycle. And right now, as you're doing nothing, going nowhere, the solar system is drifting gently in its direction. The whole apparatus, Earth, Moon, Sun, the outer planets, the entire Oort cloud, is moving toward a point near that bright blue-white star, and has been for millions of years, and will continue to be for millions more. Nobody sent an itinerary, nobody voted on it, and yet, here you all go. Pull back further, we're much further now, and something comes into view that has been sitting in the background of cosmology since its discovery in the 1970s, exerting its enormous influence in quiet gravitational silence. Something that almost swallowed a civilization's worth of astronomical certainty when it was found. Something that is still, decades later, not fully explained. The Great Attractor. This is not a metaphor or a poetic name for something mundane. The Great Attractor is a real gravitational anomaly, a region of space located approximately 150 to 250 million light-years from Earth, in the direction of the constellation Centaurus, behind the core of the Milky Way. It is an enormous concentration of mass, far larger than the individual galaxies or even galaxy clusters, that is gravitationally pulling our galaxy, the Andromeda Galaxy, and dozens of other galaxies and galaxy clusters toward it at a speed of approximately 600 kilometers per second. Not our solar system alone, not just the Milky Way, entire clusters of galaxies, the Virgo cluster, the Hydra Centaurus supercluster, possibly others, are all flowing toward this region. The discovery of the Great Attractor is one of the great detective stories of modern astronomy. In the late 1970s and 1980s, a team of astronomers known as the Seven Samurai were systematically measuring the distances and velocities of elliptical galaxies across a large region of the sky, trying to understand how galaxies moved relative to each other. They discovered that the velocities of galaxies in a large volume of space were not random. They showed a clear, systematic flow in a particular direction. Galaxies were streaming. Everything was moving towards something. Something very large was pulling. The problem was that this region of the sky, the direction toward which everything was flowing, happened to be located right behind the zone of avoidance. This is the region of the sky obscured by the dense gas, dust and stars of the Milky Way's own disk. From Earth, looking in that direction is like trying to see through a fog bank hundreds of light-years thick. For decades, the Great Attractor could be inferred from the motion it caused but not directly observed. Radio astronomy and infrared observations, which can penetrate the galactic plane more effectively than visible light, have since allowed astronomers to map the region behind the zone of avoidance. What they found was an enormous supercluster of galaxies now known as the Norma Cluster, or Abell 3627, a dense concentration of galaxies at roughly the right distance and in roughly the right direction to account for at least part of the gravitational pull. But here is the ongoing puzzle. The Norma Cluster, as massive as it is, does not seem to be sufficient on its own to explain the full extent of the observed flow. Beyond the Great Attractor, an even larger structure has been identified, called the Shapley Supercluster, one of the most massive concentrations of galaxies in the observable universe, located some 650 million light-years away, also in the same general direction of sky. Many cosmologists now believe the Shapley supercluster is a major contributor to the Great Attractor Flow, and that what was initially identified as a single gravitational source is actually the combined effect of multiple large-scale structures on an even larger cosmic scale. Historians of cosmology still argue about the extent to which the Great Attractor represents a genuine anomaly in our understanding of cosmic structure, or whether it is simply a particularly large but theoretically expected feature in the large-scale structure of the universe, the kind of giant supercluster that should exist given the initial density fluctuations of the Big Bang. The tension between these views is not entirely resolved, and the continuing discovery of even larger structures, including the Laniakea supercluster, identified in 2014, which encompasses the Milky Way, the Great Attractor, and a vast volume of surrounding space, keeps raising the question of whether the universe's large-scale structure is clumpier and more extreme than the standard cosmological model expects. The fringe tidbit here: some researchers have proposed that the motion toward the Great Attractor, combined with the recession of the universe due to cosmic expansion, means that the Milky Way is effectively approaching a boundary beyond which the cosmological expansion is fast enough to prevent any future gravitational escape. Under extreme versions of this idea, the galaxies currently flowing toward the Great Attractor are doing so in a race against time, before the accelerating expansion of the universe carries them permanently beyond each other's gravitational reach. It is worth noting that Earth itself, you, personally lying wherever you are, is participating in this flow. Every velocity in our cosmic motion profile is additive. You are spinning, orbiting the Sun, orbiting the galactic centre, and also being carried along with the Milky Way in its large-scale flow toward the Great Attractor at hundreds of kilometers per second. The Great Attractor's pull doesn't feel like anything. You don't tilt toward it when you walk. You can't point to it and feel a tug. It is doing its work entirely in the language of space-time geometry, which your body has no receptor for. Something that massive, pulling that hard from that far away, and yet here you are, completely unaware, pleasantly horizontal, getting sleepier by the minute. Everything we have described so far, the spinning, the orbiting, the galactic circuit, the bobbing, the drift toward the solar apex, the long pull toward the Great Attractor, is motion through visible matter. Through stars, gas, dust, and the gravity of things we can at least in principle detect and measure. But there is another component of Earth's cosmic journey that is arguably more important than all the visible architecture combined, and we cannot see it at all: dark matter. The term is one of the more dramatically accurate names in science. It describes something genuinely dark in both senses. It emits no light, absorbs no light, and reflects no light, and it represents a profound darkness in our understanding of the universe. We cannot observe it directly. We infer its existence entirely from the gravitational effects it exerts on things we can see. The first strong evidence for dark matter's existence came from the rotation curves of galaxies. In the 1970s, astronomer Vera Rubin and her colleagues measured how fast stars orbit at different distances from the centre of spiral galaxies. The expectation from Newtonian gravity was straightforward. Stars farther from the centre, where the visible matter is sparser, should orbit more slowly, just as the outer planets of the solar system orbit more slowly than the inner ones. What Rubin found was that they didn't. Stars at the outer edges of galaxies orbited at roughly the same speed as stars near the centre, implying that there was much more mass in the outer regions than the visible stars could account for. Something was there, massive and gravitationally real, that simply wasn't showing up in any telescope image. The current best estimate is that approximately 27% of the total mass energy content of the universe is dark matter. Ordinary, visible matter, everything made of atoms, everything you have ever seen or touched or eaten, accounts for only about 5%. The remaining 68% is dark energy, which is a related but different mystery. The universe we can see, the universe that contains all the stars and planets and nebulae and galaxies and people, is approximately a 5% sample of what actually exists. For the Milky Way specifically, dark matter is thought to constitute roughly 85 to 90% of the galaxy's total mass. It is distributed in a roughly spherical halo that extends far beyond the visible disk, far beyond the spiral arms, far beyond the warp, out into the vast dark volume surrounding the galaxy. The visible Milky Way, the beautiful pinwheel of stars and gas, is embedded within and shaped by this dark matter halo like a soap bubble floating inside a much larger invisible structure. Earth's galactic orbit, the 225 million-year circuit at 514,000 miles per hour, is not governed primarily by the gravity of the visible stars and gas of the Milky Way. It is governed primarily by the gravity of this dark matter halo. The path that Earth traces through the galaxy is determined overwhelmingly by an invisible scaffolding that we have never directly detected and do not fully understand. Dark matter also influences the shape and stability of the spiral arms, the overall structure of the galactic disk, and the large-scale streaming motions that carry the Milky Way toward the Great Attractor. The local group, the cluster of galaxies that includes the Milky Way, Andromeda, and several dozen smaller galaxies, is bound together and shaped by the combined dark matter halos of its member galaxies. The cosmic web of filaments and voids that defines the large-scale structure of the universe is, in current theoretical models, essentially the dark matter structure, with visible matter tracing the skeleton of the dark matter distribution in thin, luminous lines. What dark matter actually is remains one of the deepest open questions in physics. The leading candidates are hypothetical particles that interact with ordinary matter only through gravity, and possibly through the weak nuclear force, particles with names like WIMPs, weakly interacting massive particles, axions, and sterile neutrinos. Decades of increasingly sensitive experimental searches have not yet detected any of these candidates directly, which has led to a growing community of researchers questioning whether the dark matter paradigm is the right framework at all, whether perhaps our theory of gravity needs modification at large scales rather than requiring the existence of new particles. Historians of physics will likely describe the current period as one of productive crisis. The evidence for something like dark matter is overwhelming, but the nature of that something is entirely unresolved. The fringe observation that deserves mention here is this: if dark matter is a particle, and if it is distributed throughout the galactic disk as well as in the halo, then as the solar system bobs up and down through the disk, it would periodically pass through regions of higher and lower dark matter density. Some researchers have proposed that these periodic density variations could have detectable effects on the sun's energy output, on the heliosphere, possibly even on long-term climate patterns on Earth. The idea sits at the farthest speculative edge of dark matter research, but it is the kind of hypothesis that reminds you how much of the universe's furniture we are still in the process of inventorying. The galaxy that carries you is mostly invisible. The force that shapes your path through it is mostly undetected, and the speed at which it propels you through the cosmos was only recently precisely measured, using something as improbable as a heat map of the Big Bang. There is a recurring drama in Earth's galactic history that plays out on timescales too long for any individual consciousness to observe, but whose fingerprints are buried in the rocks beneath your feet and in the fossil record that took decades to decode. Every several tens of millions of years, the solar system drifts into and through one of the Milky Way's spiral arms, and when it does, the neighbourhood gets significantly more dangerous. The spiral arms of the Milky Way are not just prettier regions of the galaxy, they are the zones of highest stellar density, and in particular the zones of highest concentration of young, massive, hot stars, the kind of stars that live fast and die violently. Massive stars burn through their fuel in millions of years rather than billions, and when they run out of fuel, they explode as supernovae. Supernovae produce enormous bursts of cosmic rays, high-energy subatomic particles moving at close to the speed of light that can travel vast distances through the galaxy and penetrate planetary atmospheres. A sufficiently close supernova can expose the inner solar system to cosmic ray flux orders of magnitude higher than the background level we experience today. Cosmic ray exposure at elevated levels has several proposed biological consequences. Cosmic rays ionize atmospheric molecules, particularly in the upper atmosphere, and this ionization can catalyze chemical reactions that destroy ozone. Ozone depletion reduces the atmosphere's filtering of ultraviolet radiation from the sun, increasing UV flux at the surface. Elevated UV radiation damages DNA in organisms exposed to it, causing mutation rates to increase, stressing ecosystems that are sensitive to UV exposure and potentially triggering mass die-offs in certain taxonomic groups. Some researchers have proposed that this mechanism, cosmic rays from nearby supernovae or from elevated galactic cosmic ray flux during spiral arm crossings, could account for some of the extinction events and diversification episodes in Earth's paleontological record. The timing of spiral arm crossings is difficult to pin down precisely because the solar system's path through the galaxy is complex, and the arms themselves are dynamic structures that evolve over time. Estimates of when the solar system last crossed a major spiral arm vary, and the correlation with specific extinction events is, at best, statistically suggestive rather than definitively proven. Historians of paleontology and astronomy still argue with considerable force about whether cosmic factors are genuinely necessary to explain the extinction record, or whether earthbound mechanisms, volcanism, sea level change, climate shifts, bolide impacts, are sufficient without invoking galactic dynamics. The most scientifically tractable piece of evidence in this discussion is the distribution of isotopes that can serve as proxies for past cosmic ray fleets. Certain isotopes, iron-60 is the most discussed example, are produced by supernovae and accumulate in sedimentary layers when they are deposited from space. Measurements of iron-60 concentrations in deep-sea sediment cores and in lunar regolith samples show several distinct pulses of elevated iron-60 at specific times in the past, suggesting periods of elevated nearby supernova activity. One of the most studied pulses occurred roughly 2 to 3 million years ago, and has been linked by some researchers to the formation of the local bubble itself, the supernova excavated cavity we described earlier, with its supernova activity potentially coinciding with the late Pliocene early Pleistocene period, a time of significant global cooling and faunal turnover in the fossil record. The fringe contribution to this section comes from a specific but provocative correlation. Some researchers have noted that the approximate period between spiral arm crossings, on the order of 100 to 200 million years, is in the same ballpark as the timing interval between some of the major pulses in the diversification of complex life in the Phanerozoic fossil record. If true, this would suggest that the architecture of the Milky Way, the number of arms, their spacing, and the orbital parameters of the solar system is a parameter in the evolutionary history of life on Earth. Not a cause in the direct sense, but a pacemaker, a background rhythm set by galactic structure that influences, on long time scales, the tempo of biological innovation. This is, to be clear, a hypothesis with substantial uncertainties attached to it. The fossil record is incomplete, the timing of arm crossings is imprecisely known, and the causal mechanisms proposed are indirect. But the general principle, that Earth's biological history is not independent of its galactic context, is no longer considered fringe in the way it would have been 50 years ago. Astrobiology, the field that studies the relationship between cosmic environments and the conditions for life, now routinely considers galactic-scale factors alongside planetary ones. What this means in practical terms is something like this. The fact that you exist, that complex multicellular intelligent life evolved on this planet, is not entirely a matter of local conditions. It is partly a matter of where in the galaxy the solar system has travelled and what it has encountered along the way. The mass extinctions that cleared ecological space for mammals, and eventually for primates, and eventually for humans, may carry the fingerprints of galactic dynamics alongside the more familiar stories of asteroid impacts and volcanic eruptions. You're not just the product of Earth's history, you are, in a small but real sense, the product of Earth's galactic history. Not everywhere in the Milky Way is a good place to be. This is a deceptively important statement, and one that has gained enormous traction in astrobiology over the past 2 decades, as researchers have begun to seriously map the galaxy, not just in terms of stellar populations, but in terms of habitability, the conditions necessary for complex life to arise and persist. The concept is called the Galactic Habitable Zone, and it carries an explicit analogy to the familiar circumstellar habitable zone, the range of distances from a star where liquid water can exist on a planet's surface. The galactic habitable zone is the range of distances from the galactic centre where the conditions for complex life are adequately met. Too close to the centre, and the environment becomes lethally hostile. Too far from the centre, and a different set of problems emerge. Near the galactic centre, the problems are numerous and severe. The stellar density is enormously higher than in our part of the galaxy. Stars are packed so tightly that close stellar encounters, which could disrupt planetary orbits and bombard solar systems with perturbing gravitational influences, would occur on timescales of tens of millions of years, rather than the billions of years scales typical in our neighbourhood. Supernova rates near the centre are far higher, given the higher stellar density. The supermassive black hole Sagittarius A star at the galaxy's core, while currently relatively quiescent, periodically produces energetic outbursts, and a much earlier, more active phase of the black hole's history would have bathed the inner galaxy in lethal radiation. The intense X-ray and gamma-ray environments near the galactic centre would make sustained atmospheric chemistry and biological molecular stability very difficult to maintain. The outer galaxy has a different problem: poverty. Stars in the outer reaches of the Milky Way are, on average, significantly older and have much lower metallicity, which in astronomical terminology means they contain lower abundances of elements heavier than hydrogen and helium. This matters because planets, and particularly rocky terrestrial planets like Earth, are built from heavy elements: oxygen, silicon, magnesium, iron, and the whole suite of elements forged in generations of previous stars and distributed into the interstellar medium by supernova explosions. In the outer galaxy, where metallicity is low because there have been fewer generations of star formation to enrich the interstellar medium, the raw materials for terrestrial planet formation are correspondingly scarce. Complex chemistry, which life requires, depends on the availability of carbon, nitrogen, oxygen, phosphorus, and other heavy elements in sufficient quantities. Our solar system sits at a galactic radius of about 26,000 to 28,000 light-years from the centre, roughly 2/3 of the way out in the disk. This turns out to be a statistically lucky position. It is outside the dangerously dense inner regions with their elevated supernova rates and radiation environments, but inside the metal-poor outer regions, where planetary formation would be chemically impoverished. It is also, as noted in earlier sections, currently between the major spiral arms, in a relatively calm inter-arm region, with lower cosmic ray flux and fewer disruptive stellar encounters. The inter-arm location, combined with the moderate galactic radius, places the solar system in a particularly calm stretch of the galaxy at this point in its orbit. The galactic habitable zone was first formally proposed in a 2004 paper by Charles Lineweaver and colleagues, and it has been refined, debated, and extended by subsequent work. One of the interesting complications is the time dimension. The habitable zone has not been fixed throughout the galaxy's history. Early in the Milky Way's history, the overall metallicity was lower everywhere, and the supernova and active galactic nucleus activity was much higher, making the entire galaxy less hospitable to complex life. The habitable zone has effectively been expanding over cosmological time as the galaxy has matured, the heavy element content of the disk has increased, and the violent early activity has subsided. Earth formed at a time roughly in the middle of the galaxy's history, when conditions in our galactic neighbourhood had become conducive to terrestrial planet formation, but before the galaxy had aged to the point where stellar populations in the relevant zone were predominantly old and quiescent. Historians of astrobiology still argue about whether the galactic habitable zone is a sufficiently constrained concept to make meaningful predictions, or whether the uncertainties in the relevant parameters, the precise distribution of heavy elements, the timing and frequency of nearby supernovae, the detailed history of galactic habitable zone evolution, are large enough that the concept is more illustrative than predictive. The field is young enough that these debates are still productively generating new research, rather than settling into consensus. The fringe idea worth noting here is the rare Earth hypothesis, the proposal, advanced by Peter Ward and Joe Kirschvink, that the combination of circumstances that produced complex life on Earth is so specific and so unlikely to be replicated elsewhere that intelligent life may be extraordinarily rare in the universe, despite the abundance of planets. The galactic habitable zone is one of several filters in the rare Earth argument. Even if Earth-like planets are common, the fraction of them located in the galactic habitable zone, in the right portion of the galaxy, at the right time in the galaxy's history, is potentially quite small. You're in the right place. In all the volumes of the galaxy where complex life faces overwhelming obstacles, in the radiation-bathed galactic centre, in the metal-starved outer disk, in the crowded spiral arms, you happen to be in the rare zone where all the numbers worked out. Your address in the galaxy is not incidental to your existence. It is part of the reason for it. Everything so far has been presented in the comfortable, intuitive language of everyday physics. Speeds, distances, directions, orbital periods. These are the concepts of Newtonian mechanics, the framework that works so well for everyday experience and even for most astronomical purposes that its limitations are easy to forget. But moving at the speeds involved in Earth's cosmic journey, particularly the 514,000 miles per hour of the solar system's galactic orbit, opens a door into a different framework, one that is simultaneously more fundamental and more deeply strange: Einstein's special relativity. The central claim of special relativity is this: the laws of physics are the same for all observers in uniform motion, and the speed of light is the same for all such observers, regardless of their relative motion. This sounds innocuous until you follow its logical consequences, which include time passes at different rates for objects moving relative to each other, lengths contract in the direction of motion, and mass increases with velocity. These effects are not tricks or illusions or philosophical subtleties. They are physically real, have been measured experimentally with extraordinary precision, and are incorporated into the design of GPS systems, particle accelerators, and any other technology that requires precise timing at high speeds. The degree to which these effects operate depends on the ratio of an object's velocity to the speed of light, a ratio denoted by the Greek letter beta. At everyday human speeds, this ratio is so tiny that relativistic effects are completely negligible. At the speed of light itself, they become infinite. At the speed of the solar system's galactic orbit, the ratio is approximately 0.0007. That is, about 0.07% of the speed of light. At this ratio, the relativistic effects are real but small. The relevant quantity for time dilation, how much more slowly a moving clock runs compared to a stationary one, is determined by the Lorentz factor, gamma, which for Earth's galactic orbital speed equals approximately 1.00000245. This means that for every billion seconds of time that passes for a hypothetical, truly stationary observer, someone on Earth, moving with the solar system in its galactic orbit, would experience only about 999,755 seconds, a difference of about 245 seconds per billion seconds, or about 4 minutes per billion seconds. Over the age of the solar system, approximately 4.5 billion years, this time dilation accumulates to roughly 18 minutes of difference. Earth, by virtue of its galactic motion, has experienced approximately 18 minutes less time than a hypothetical observer who remained perfectly stationary relative to the cosmic microwave background. This is, on one hand, a vanishingly small effect by any practical standard. On the other hand, it is real, measurable in principle, and represents something profound: the fact that space and time are not separate, absolute quantities, but are woven together into space-time, and motion through space is simultaneously motion through time. When you add the orbital velocity around the Sun, Earth's rotational velocity, and the full combined motion relative to the CMB, approximately 1.3 million miles per hour, or about 0.2% of the speed of light, the time dilation effect grows to something slightly more significant but still small. At 0.2% of the speed of light, the Lorentz factor is approximately 1.000002, meaning roughly 2 microseconds of time dilation per second. Over a human lifetime, this accumulates to a few minutes of difference. The fringe connection worth drawing here is between time dilation and the nature of biological aging. If organisms on Earth are running on a time that is very slightly dilated relative to absolute cosmological time, and if the biochemical processes of aging are governed by the number of absolute time units that pass rather than the number of local time units, then, in an extraordinarily small and practically meaningless way, motion through space might have an effect on the rate of biological aging relative to cosmological timekeeping. This is not a claim that space travel makes you younger in any medically significant sense at everyday speeds. It does not. But it is a reminder that the connection between motion and time is a physical fact rather than a philosophical abstraction. The mainstream historical note here is that Einstein published the special theory of relativity in 1905 in a paper titled On the Electrodynamics of Moving Bodies, as part of a remarkable year in which he also published the paper introducing the quantum of light, the photon, and the paper deriving E equals mc squared. He was 26 years old and working as a patent examiner in Bern, Switzerland, with no academic position and no laboratory. Historians of science still argue about the degree to which Einstein was aware of and influenced by the experimental results of Michelson and Morley, who had failed to detect the motion of the Earth through the hypothetical luminiferous ether in 1887, a negative result that had been haunting physics for 2 decades before Einstein's elegant theoretical resolution of the underlying conceptual problem. You're moving fast enough through the galaxy that space-time is, by a hair's breadth, bending around you. Your clocks are running by a nearly imperceptible degree slower than those of any hypothetically stationary observer. This is not poetry. It is physics, and it applies to you right now as your eyelids grow heavy and your breathing slows. And now we arrive at the question that, once asked, tends to spin quietly in the background of consciousness and refuse to be fully answered. Relative to what exactly is anything moving? This is not a trivial question. It is in fact one of the most important questions in the history of physics, and the process of answering it, or discovering why it can't be fully answered, transformed our understanding of the universe more than almost any other inquiry. Let's start with what you already know intuitively. Motion is relative. You're sitting on a train and the train is moving. Relative to the ground, you're moving at 70 miles per hour. Relative to the seat next to you, you are not moving at all. Relative to another train passing in the opposite direction at 70 miles per hour, you're moving at 140 miles per hour. None of these descriptions is more fundamentally correct than any other. They are all valid, each within its own reference frame. This is the basic principle of Galilean relativity, understood in its essential form since the 17th century. Now apply this to Earth. Earth is moving relative to the Sun, but the Sun is moving relative to the Milky Way. The Milky Way is moving relative to the Virgo supercluster. The Virgo supercluster is itself moving in the larger cosmic structure. At each level of zoom, the reference frame you are using expands and a new motion becomes visible. Is there a level at which you can finally say, this is the real reference frame, this is absolute rest? This is the baseline against which all other motions are truly measured? In Newtonian physics, the answer was nominally yes. Newton's mechanics implied a framework of absolute space, a fixed, universal backdrop against which real motions occurred. Objects in absolute rest were truly at rest. Objects moving through absolute space were truly moving. The problem was that Newton himself couldn't identify where this absolute space was or how to detect it experimentally. It was a logical necessity of his system that remained empirically inaccessible. The search for absolute space culminated in the Michelson-Morley experiment of 1887, the experiment that failed to find evidence of the luminiferous ether the hypothetical medium that was supposed to fill absolute space and through which light was supposed to propagate. The null result of this experiment, famously referred to as the most important negative result in science, implied that there was no detectable absolute space through which Earth moved. Einstein's special relativity, 18 years later, formalized this. There is no preferred, absolute reference frame. All uniformly moving frames are equivalent. Absolute rest is not a physically meaningful concept, and yet there is a sense in which the universe does provide something that functions as a global reference frame, and it is the same ancient light that will appear in the next section in a different role. The cosmic microwave background, the faint afterglow of the Big Bang, permeating every direction of the universe, defines, in practice, if not in absolute principle, a reference frame against which motions can be measured. An observer who is truly at rest relative to the CMB would see it as perfectly uniform in every direction, with no variation in its apparent temperature. Any observer who's moving relative to the CMB will see it as slightly hotter in the direction of motion and slightly cooler in the opposite direction. The same Doppler effect that makes an ambulance siren change pitch as it passes. This measured temperature asymmetry in the CMB is how astronomers have determined the actual speed of the solar system relative to the largest available reference frame. The result is approximately 620 kilometers per second, about 1.38 million miles per hour, in the direction of the constellation Leo. This is the sum of all the motions we have been adding up. Earth's orbital velocity around the Sun, the Sun's orbital velocity around the galactic centre, and the peculiar velocity of the Milky Way relative to the CMB, which itself reflects the large-scale streaming motion toward the great attractor and whatever lies beyond it. The philosophical significance of this measurement is worth dwelling on. Even in a relativistic universe where absolute rest is not a physical concept, the CMB provides the closest thing to a cosmic background, a reference against which the total motion of everything in the observable universe can be at least approximately compared. The fact that the solar system is moving at 1.38 million miles per hour relative to this background means that from the perspective of the universe's oldest light, Earth is nowhere near still. Historians of philosophy still argue about whether the CMB frame is privileged in any meaningful sense, whether the fact that it's defined by the afterglow of the Big Bang gives it a special status that pure relativistic philosophy should deny. The most common resolution is pragmatic. The CMB frame is not privileged in the physical sense of being absolutely preferred by the laws of physics, but it is observationally convenient and cosmologically natural as a reference. The way sea level is not the only altitude, but is a sensible one to measure from. The question relative to what turns out to have an answer that is simultaneously specific and unsatisfying, relative to the universe's own thermal memory. You're moving at 1.38 million miles per hour relative to the echo of the moment everything began. And there is as yet nothing outside the universe to serve as a more fundamental reference. The cosmic microwave background is one of the most extraordinary objects in science. It is not an object in the usual sense. It is a field, a pervasive radiation filling every corner of the observable universe with almost perfect uniformity. But in terms of what it has revealed about the nature of the cosmos, it functions as a kind of master key, unlocking not just the history of the universe, but as we just discussed, a measurement of Earth's total velocity through the cosmos. Let's understand what it actually is, because the name alone gives very little away. About 380,000 years after the Big Bang, a number that sounds large but is tiny compared to the current age of the universe at 13.8 billion years, the universe had cooled enough for electrons to combine with protons and form neutral hydrogen atoms for the first time. Before this moment, the universe was a hot, dense plasma, and photons, particles of light, could not travel more than a tiny distance before being scattered by free electrons. The universe was opaque. After this moment of recombination, the slightly misleading name given to this process, the universe became transparent, and the photons that had been trapped in the plasma were suddenly free to travel. They have been travelling ever since, for 13.4 billion years, spreading in all directions, gradually losing energy as the universe expanded around them. Their original temperature of about 3000 Kelvin has redshifted down to 2.725 Kelvin. They now constitute the CMB, the oldest light in the universe, arriving at Earth from every direction of the sky. The CMB was first detected in 1965 by Arno Penzias and Robert Wilson, who were using a radio antenna in New Jersey and kept finding an annoying, persistent background hiss that they initially thought might be pigeon droppings in the antenna receiver. They cleaned the antenna, the hiss remained, and they eventually shared the Nobel Prize in Physics for the discovery. The detection of the CMB was one of the most important confirmations of the Big Bang model, and effectively ended serious scientific consideration of the steady-state model of the universe. The CMB's use as a cosmic speed camera, revealing Earth's velocity through the universe, relies on a precise measurement of its temperature asymmetry across the sky. In 1977, using instruments aboard a U-2 aircraft, astronomers measured the CMB dipole, a pattern in which one side of the sky is slightly warmer and the opposite side is slightly cooler by about 1 part in 1,000. This pattern is exactly what would be expected if the observer is moving relative to the CMB source, a large-scale Doppler effect. The direction of the warm spot gives the direction of motion. The magnitude of the temperature difference gives the speed. The result: the solar system is moving at approximately 620 kilometers per second, about 1.38 million miles per hour, in the direction of the constellation Leo/Crater. This motion, called the CMB dipole velocity, or sometimes the peculiar velocity of the local group, represents the cumulative effect of the Sun's galactic orbit, the Milky Way's motion within the local group, and the local group's motion in the larger scale flow toward the Great Attractor and the Shapley supercluster. The CMB is also the source of one of the most famous and haunting images in modern science. The full sky maps produced by the COBE satellite in the 1990s, the WMAP satellite in the 2000s, and the Planck satellite in the 2010s. These maps show the CMB temperature across the entire sky at extraordinary precision, and the small temperature variations they reveal, the lumpiness of the early universe at the level of a few parts in 100,000, are the seeds from which all the structure in the universe, all the galaxies, clusters, filaments and voids, grew under gravity over 13.8 billion years. The fringe connection here is a peculiar anomaly known as the CMB cold spot, a region of the sky in the direction of the constellation Eridanus that is significantly colder than the average CMB temperature and significantly larger than standard cosmological models predict. Some researchers have proposed that this cold spot might be explained by a supervoid, a region of space containing less matter than average, along the line of sight. Others have entertained more exotic explanations, including the intriguing but speculative possibility that the cold spot represents an imprint of a collision between our universe and a neighbouring universe in a hypothetical multiverse. Historians of cosmology will note that this last explanation received an unusual amount of popular press coverage for a hypothesis that remains, at best, a speculative fringe idea. But it has not been definitively ruled out, and the cold spot's cause remains an active area of research. Tonight, the universe's oldest light is falling on your windows, your walls, your skin. It has been travelling since before stars existed, since before the first galaxies had formed, since before the first heavy elements had been forged in the first stellar cores. It passes through your house, through your roof, through your blanket, and through you, carrying within its temperature pattern the complete history of your motion through the cosmos like a receipt. 4.5 billion years from now, give or take, Earth's galactic address is going to change in a very dramatic way. Everything we have described so far, the smooth galactic orbit, the gentle bob through the disk, the drift toward the solar apex and the great attractor, all of it is predicated on the Milky Way continuing to exist as the Milky Way. And on current astronomical measurements, it will not. The Andromeda Galaxy is coming. Andromeda, also known as M31, the 31st entry in Charles Messier's 18th century catalogue of objects that look like comets and weren't, which is honestly the least glamorous naming origin for one of the most important objects in astronomy, is the nearest large galaxy to the Milky Way. It's approximately 2.537 million light-years away, a number that is large enough to seem safely astronomical, and is, in fact, not large enough at all. Andromeda is the most distant object visible to the naked eye from Earth. On a dark, clear night, it appears as a faint smudge in the constellation Andromeda, an elongated glow barely distinguishable from the background sky. What you're seeing when you look at that smudge is approximately 1 trillion stars, and they are approaching at about 110 kilometers per second, roughly 250,000 miles per hour, directly toward us. The collision, or more technically the merger, is expected to begin in approximately 4 to 5 billion years. The precise timeline depends on Andromeda's transverse velocity, which is much harder to measure than its line-of-sight velocity. For a long time, it was uncertain whether Andromeda was on a direct collision course or whether it might graze past the Milky Way. Precise measurements from the Hubble Space Telescope, published in 2012, determined the transverse component of Andromeda's velocity well enough to establish that a direct merger is essentially certain. What happens during a galaxy merger is not the violent, fiery collision that the word collision implies. Galaxies, for all their vast size, are mostly empty space. The distance between individual stars within a galaxy is so enormous that during galaxy merger, the probability of any two individual stars actually colliding is extremely low, essentially zero for most stars. The merger is a gravitational event, not a physical pile-up. The two galaxies pass through each other, their stars intermingling gravitationally, their orbital structures disrupted by the gravitational interaction, and the whole messy system gradually settling over hundreds of millions of years into a new, merged galaxy. The current models suggest that the merger product, sometimes called Milkomeda in popular science writing, would be an elliptical galaxy rather than a spiral, as the organised disk structures of both galaxies are scrambled by the merger process. During the merger, the Sun and Earth are expected to be flung into very different orbits. The current models suggest that our solar system's orbit will be significantly perturbed, possibly thrown to a much larger galactic radius, possibly incorporated into one of the elongated tidal tails that form during galaxy mergers. The probability of the Sun being flung entirely out of the merged galaxy is estimated at a few percent. The probability of any stellar collision or close enough encounter to disrupt the planetary system is vanishingly small. Earth will almost certainly survive the merger physically intact, though by that point, the Sun will be significantly older and hotter, presenting its own existential challenges to any life that might still exist here. The historical note here involves Edwin Hubble, who established in 1923 that Andromeda was a separate galaxy entirely, rather than a nebula within the Milky Way, by identifying a particular type of pulsating star, a Cepheid variable, in its outer regions and using its known brightness to calculate an actual distance. Before Hubble's measurement, the great debate between astronomers Harlow Shapley and Heber Curtis over whether spiral nebulae were distant galaxies or nearby structures within the Milky Way had been unresolved for years. Historians of astronomy still argue about the degree to which this debate was settled cleanly by Hubble's evidence, or whether the resolution was more gradual and contested than the popular narrative suggests. The fringe thought for this section is genuinely cosmic in its scale. The Andromeda collision will not be unique. On even longer timescales, the Milky Way and the other members of the local group, Andromeda, Triangulum, and the 50-odd dwarf galaxies orbiting them, are likely to merge into a single, large elliptical galaxy. And on truly cosmological timescales, the accelerating expansion of the universe will eventually carry all other galaxy clusters beyond our cosmological horizon, leaving the merged local group in isolation, the last island of light in an increasingly empty, cold, dark universe. The star formation in the merged galaxy will eventually cease as the gas supply is exhausted. The stars will one by one burn out. The last red dwarfs will gutter out after trillions of years, and whatever remains of the universe's matter will slowly, patiently disintegrate. But that is a very long way off. Tonight, Andromeda is just a faint smudge, 2.537 million light-years away, heading this way on a schedule that gives you roughly 4 billion years to make peace with it. That seems like plenty of time. The story of how we came to know all of this, how human beings anchored to a small rocky planet, orbiting an unremarkable star, managed to determine Earth's speed through the galaxy, map the structure of the Milky Way from the inside, discover the Great Attractor, measure the cosmic microwave background, and calculate the precise trajectory of the galactic merger 4.5 billion years hence, is itself one of the most remarkable intellectual achievements in the history of our species. It did not happen in a single flash of insight. It accumulated over centuries through an overlapping series of incremental discoveries, each one building on the last, each one enabled by new tools and new mathematical frameworks that the previous generation had lacked. The long prologue stretches back at least to Nicholas Copernicus, whose heliocentric model of the solar system, published in 1543 in the final year of his life, dislodged Earth from the centre of the cosmos and began the process of putting it in motion. Galileo's telescopic observations in the early 1600s provided concrete observational support for a moving Earth. Johannes Kepler's mathematical laws of planetary motion, derived between 1609 and 1619, described the orbital ellipses and the relationship between orbital period and distance with remarkable precision, using only observational data and mathematical inference. No physical mechanism, just empirical law. Isaac Newton's gravitational theory in 1687 provided the mechanism unifying the motions of planets and moons and falling apples under a single mathematical framework that would serve as the foundational language of celestial mechanics for the next 200 years. William Herschel's detection of the sun's motion through the local stellar neighbourhood in the 1780s, described earlier, was a decisive step, the first direct evidence that the sun itself was not stationary. But the full scope of the sun's motion, not just relative to nearby stars but in a grand orbit around the galaxy, required knowing that the Milky Way was a galaxy, a distinct bounded island of stars in a much larger universe. That realization came only in the early 20th century through the work of Henrietta Swan Leavitt, who discovered the period luminosity relationship of Cepheid variable stars, the cosmic distance ladder rung that Edwin Hubble later used to measure the distance to Andromeda. Leavitt's contribution, made while working as a human computer at the Harvard Observatory analysing photographic plates, was foundational to extragalactic astronomy. And the fact that she was not credited or recognised during her lifetime with the full magnitude of her contribution is one of the more uncomfortable chapters in the history of science. Harlow Shapley in the 1910s used Cepheid variables and globular clusters, the ancient dense spherical clusters of stars that swarm in the halo around the Milky Way, to determine that the centre of the galaxy was not near the Sun but in the direction of Sagittarius, roughly 26,000 light-years away. This was the first measurement of the Milky Way's scale, and it corrected the long-held assumption that the Sun was near the galactic centre. It was not a comfortable finding. It demoted the Sun from a central position it had been implicitly assigned by default. Through the mid-20th century, radio astronomy opened the galactic plane to systematic mapping for the first time. The neutral hydrogen atom emits a characteristic radio signal at a wavelength of 21 centimeters, and this emission can penetrate the dust that blocks visible light. Radio astronomers in the 1950s and 1960s used 21 centimeter observations to trace the distribution of hydrogen gas throughout the galactic disk, revealing the spiral structure and confirming that the Milky Way was a spiral galaxy, though, as noted, the precise nature and number of the spiral arms has been contested ever since. The discovery of the Great Attractor's gravitational flow in the 1970s and 1980s required measuring the peculiar velocities of thousands of galaxies, a painstaking, years-long program that combined photometric and spectroscopic observations with careful calibration of distance measurement methods. The Seven Samurai group who identified the large-scale flow were working at the edge of what the instrumentation of their era could accomplish. The modern era of galactic mapping began with the launch of the Hipparcos satellite in 1989, which measured the positions and distances of over 100,000 stars with unprecedented precision, and reached a new peak with the Gaia satellite, launched in 2013 by the European Space Agency. Gaia has measured the positions, distances, velocities, and other properties of over 1 billion stars, more than any previous catalogue by orders of magnitude, creating a three-dimensional map of our galactic neighbourhood of extraordinary precision. Analysis of Gaia data is still ongoing, and each new data release produces a wave of new discoveries and revised understandings of the Milky Way's structure and dynamics. The fringe note here belongs to an ongoing debate in the history and philosophy of science. To what extent is our current model of the Milky Way structure, including its spiral arms, its bar, its halo, the dark matter distribution, a discovery of a pre-existing reality, and to what extent is it a construction shaped by the instruments, methods, and theoretical assumptions we brought to the problem? The question is more than philosophical. Practical choices about which model to use when designing future space missions or interpreting cosmological surveys have real consequences. What is not in question is the extraordinary trajectory, from a civilization that believed the sun went around the Earth, to a civilization that has mapped 1 billion stars and measured the temperature of the oldest light in the universe, it took about 500 years, in galactic terms roughly 2 milliseconds. There is a version of this information that is supposed to be terrifying, and every now and then, in casual conversations about astronomy, someone delivers it that way, leaning forward across the table with a particular gleam in their eye, laying out the numbers, the 514,000 miles per hour, the Great Attractor, the Andromeda collision, the eventual heat death, waiting for the moment of existential vertigo to land. It sometimes does. The scale of it when it hits can feel genuinely annihilating. But that is not the only way to receive it, and it's worth spending a little time before we ease into the wind down, thinking about what it might mean for you to know all this, not as a fact set to be filed away, but as a genuine feature of the reality you live in. You're moving at 1.38 million miles per hour through the cosmos right now. You're doing this automatically, passively, without expenditure of effort or fuel. The universe is providing the motion. You're simply the passenger. There is something almost restful in this, if you let yourself feel it rather than calculate it. You don't have to go anywhere. You're already going everywhere. The cosmic journey is built in. The layers of motion we've described, the daily spin, the annual orbit, the galactic circuit, the bob through the disk, the drift toward the solar apex, the sweep toward the Great Attractor, are not chaos. They are deeply structured. They follow laws of physics that are among the most rigorously tested and repeatedly confirmed descriptions of reality that human beings have ever produced. The gravitational equations that govern Earth's orbit around the Sun also govern the Sun's orbit around the galactic centre. The dark matter halo that shapes the Milky Way obeys the same mathematical description of gravity as the Moon orbiting Earth. The universe is lawful, not in the sense of being simple or easy to understand, but in the sense of being consistent, regular, and in principle comprehensible. This lawfulness is part of why we can be here at all. The stability of Earth's orbit, maintained over billions of years in its current form, is what allowed complex life to evolve. Life requires long timescales, and long timescales require stable environments, and stable environments require predictable, repeating physical processes operating under consistent laws. The fact that gravity works the same way today as it did when the first bacterial cells were learning to photosynthesize in ancient oceans. The fact that the Milky Way has not flung the solar system into the void, or sent it careening into a dense spiral arm at the wrong moment, or allowed a runaway chain of nearby supernovae to strip away Earth's atmosphere, is not trivial. It is one of the necessary preconditions of your existence, and it has been reliably in place for 4.5 billion years. There is also something worth acknowledging about the strangeness of your position in this story. You are the part of the universe that knows the universe is moving. The motion we've described, the spinning, the orbiting, the galactic speed, the CMB velocity, was happening long before any mind evolved on Earth to notice it. The first photosynthetic bacteria were hurtling around the galactic centre at 514,000 miles per hour, with no possibility of knowing it. The dinosaurs were doing it for 165 million years without a single one of them formulating a question about it. The universe went about its business for 13.8 billion years, most of that time in a form that had no consciousness to observe it. And then, in the last eye blink of cosmic time, on a small rocky planet in an unremarkable corner of a mid-sized galaxy, matter organized itself into configurations capable of asking, "Where am I? And how fast am I going? And what does it mean?" The answer to the first question, 2/3 of the way out in the Milky Way, inside a bubble blown by ancient supernova, in the Orion Arm, in a galactic habitable zone, at coordinates that required extraordinary coincidences of cosmic history to produce. The answer to the second question, 1.38 million miles per hour, give or take, relative to the oldest light in the universe. The answer to the third question, that is what all the best minds of all the centuries have been working on, in various forms, and the answer is still in progress. What is not in progress, what requires no further calculation, is the immediate intimate fact that all of this motion, all of this cosmic machinery, is currently carrying you through the galaxy as you lie wherever you are tonight. Your body is being borne on it the same way a leaf is borne on a river, without effort, without consultation, as a natural and unremarkable feature of existing in a universe that moves. The leaf doesn't know the river, but you do. You know the river's speed, its direction, its history, its eventual destination. You know the shape of the bed it flows through, the forces that carved it, the darkness at its edges. You know things about your own cosmic passage that no one, anywhere in the observable universe, could have known until very recently in the history of everything, and knowing it, you can close your eyes. The motion doesn't require your attention to continue. The galaxy will carry you faithfully, at exactly the speed it always has, all night long. You don't need to navigate, you don't need to steer. You are already, and without any effort whatsoever, exactly where you're supposed to be. And now, gently, we let the numbers go. You don't need to hold them anymore. The million miles per hour, the 225 million years, the 26,000 light years to the galactic center, the 4.5 billion years to the Andromeda merger. They have done their work. They have opened a door in the back of your mind that looks out onto something vast and patient and quietly magnificent. You can leave that door open now and let the cool air from it move through you as you drift. You're lying still. The room around you is dark or close to it. Maybe there's a soft light somewhere, the pale rectangle of a window or a standby glow from some device that doesn't quite know how to fully rest. The world outside has settled into its nighttime sounds, the distant murmur of traffic perhaps, or the small creaking of a house adjusting its weight in the dark, or the wind moving through whatever trees grow near where you sleep. All of it is moving. The trees are moving, the house is moving, you are moving. The planet carrying all of you is spinning, slowly and faithfully, turning that part of the sky where you're away from the sun and toward the night. It has done this every single night for 4.5 billion years. It did it when there was nothing here but ocean and volcanic rock. It did it through the first explosion of life, through the great extinctions, through the long ages of the dinosaurs, through the rise of the first small cautious mammals who would eventually become your ancestors. It did it through every human night that has ever occurred, every sleep of every person who ever lived. And it is doing it tonight for you, with the same patient indifference and complete reliability. The galaxy outside is wheeling in its slow, enormous circuit, the one that takes 225 million years to complete, the one that has no observer other than the universe itself, the one that carries no passengers who know about it except the ones on this particular planet, in this particular moment of cosmic history. That circuit is not hurrying. It has nowhere urgent to be. It will continue long after the last human thought has occurred, and long after that, and longer still. Let the great attractor pull at whatever it pulls. Let Andromeda begin its 4 billion year approach. Let the solar system bob, unhurried, above the galactic plane. Let the CMB carry its ancient temperature map through every wall and every ceiling and every closed eye on Earth. None of it requires anything from you tonight. None of it is asking. Your breathing is slower now, probably. The thoughts that were spinning when you started this journey have, if the night has been kind to you, started to lose their sharpness. The worries and the lists and the half-formed plans that follow most of us to bed. The galaxy is too large and too old for most worries to feel proportionate to it, and that is perhaps one of the most practical gifts that astronomy offers, a scale reference that gently and without malice puts almost everything in its place. You are made of atoms that were forged in stars that died before the sun was born. You are breathing air that has been breathed by every creature that has lived on this planet since the atmosphere became breathable. You're lying on a rock that has been travelling the galaxy for 20 cosmic years, that has been warmed by the same star every morning for 4.5 billion of them, that has somehow, against every statistical expectation, managed to produce the conditions for something as complicated and as improbable as a mind that can wonder about all of this. That is not a small thing. That is, by any reasonable measure, an extraordinary thing. And it happened here, on this moving rock, in this improbable corner of this warped and lumpy and dark matter-threaded galaxy, at this moment in cosmic time. You don't have to do anything with this. You don't have to resolve it or understand it fully or respond to it in any particular way. You just have to be here, which you are, effortlessly and automatically, the same way the planet is here, carried along by physics, patient, unhurried, arriving and departing in the ordinary rhythm of breath and heartbeat and the slow turning of the world. The stars are out tonight, wherever you are. You can't see most of them. The light of the galaxy is too diffuse, the distance too vast, the human eye too small, but they're there, as they always are. All 400 billion of them in this galaxy alone, all of them moving, all of them obeying the same ancient equations, all of them participating in the same grand and unhurried circuit around the centre of everything. You are part of that circuit. You always have been. You always will be. Close your eyes now. The galaxy has you. It knows where it's going, and wherever that is, you'll be there too. Rested, quiet, carried gently through the dark at 1.38 million miles per hour, which is, it turns out, a perfectly comfortable speed at which to fall asleep. Good night.